Hello friends. IBM is here with another episode of Learning Physics, and today I would like to take you to episode 2 of oscillations and simple harmonic motion. Remember, this is Physics 9702. This is Physics 9702 Cambridge. That is actually paper 4. Oscillations and simple harmonic motion, that is paper 4. This is the last topic in paper 4 according to these solved past paper questions. That means all the topics according to the syllabus for examinations starting 2022. All the topics will have been recorded, at least with some questions recorded. So do not forget to download the document which is attached in the video description. In case you don't have it, print the document and practice in hard copy. Remember, because you're going to do exams in hard copy, it's better you practice in hard copy so that you practice on the printed document so that you gain a lot of experience. So today I want us to move to part 2. I think simple harmonic motion will have a few more parts, maybe 4, 5, I don't know. But whatever it is, it will come to an end. So throughout these videos of simple harmonic motion and oscillations, we are going to see questions relating to the types of oscillations, simple harmonic motion, forced damped oscillations, energy of oscillations. We shall see some graphs like we have already seen graphs in part 1. Resonance will not miss, and of course, and so many others that I've called etc. So without wasting much time, I want us to move straight away to our past papers, our document of past papers. And this is, I think in part 1, we stopped on page 331, 30. So we should move 331. The first question, let me try to reduce the thickness. A ball is held between two fixed points A and B by means of two stretched springs as shown here. You'll see such questions several times. The ball is free to oscillate along the straight line AB. The springs remain stretched and the motion of the ball is simple harmonic motion. Remember, if the motion is simple harmonic motion, acceleration is equal to negative omega squared x. That is, acceleration is directly proportional to displacement, and the minus indicates that the acceleration and the displacement are always in opposite directions. The ball is free to oscillate along the straight line AB. The spring remains stretched and the motion of the ball is simple harmonic. I think this is a repetition. The variation with the time t of the displacement x of the ball is from its equilibrium position is shown here. So this is, of course, this is simple harmonic motion because you notice that even the amplitude remains constant throughout the motion. Use the figure to determine for the oscillations of the ball the amplitude. Remember, amplitude is the maximum displacement. So I just look at the graph. So the scale here on the vertical is 0.1 because there are 10 small squares. So this is actually 1.7 centimeters. So the amplitude in centimeters is 1.7. Then the frequency, remember frequency is equal to 1 over period. So we need the period. From the graph, we need the period. Period is the time for one complete oscillation. So I have to look for a more convenient point for me to find the correct period. So I can see that when I look at this peak here and this peak here, it is easier for me to find the period. So I just need to know what this is. The scale on the x-axis, there are 10 small squares in a unit of 0.2. So the scale on the x-axis is 0.2 divided by 10, which is 0.02. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 small squares, so I multiply 0.02 times 9, which is 0.18, I guess. Where is my calculator? So this value is 0.18. Then I will check this one. 1, 2, 3, 4, 5, 6, 7. 7 small squares from 0.4. So I will say 0.202 times 7, I add this to 0.4. So 0.02 times 7 plus 0.4. So this is 0.54. Now I want the period, so that is the time between this point here and the other point. So I will have 0.54 minus 0.18, and I'm getting 0.36. So the period is 0.36 seconds. So I find the frequency, 1 divided by the answer, that is 2.78, or approximately 2.8 hertz. So that is the frequency. The challenge will be reading the value of t correctly and finding the correct answer. Show that the maximum acceleration of the ball is 5.2 meters per second. So we have already said if the acceleration is if the motion is sympharmonic, acceleration is negative omega squared x, and we already know that omega is equal to pi divided by the period, or 2 pi f, where f is the frequency and f is 1 over t. So we just substitute. The acceleration a is going to be negative. Of course, I will ignore the negative in calculation. So this will be 2 pi divided by the period, which is 0.36, and this should be squared times. We want maximum acceleration. Acceleration is maximum when displacement is maximum because they are directly proportional. So this will be times 1.7, but it is in centimeters, times 10 power negative 2. So I check my calculator. So from my calculator, I'm getting 5.2. This is 5.178, which is approximately 5.2 meters per second squared, as required. Use your answers in A to plot on the axis of the figure 3.3 the variation with the displacement x of the acceleration A of the ball. We want a variation with the displacement. Remember, the maximum acceleration is 5.2. So I will say A naught, that is maximum acceleration is 5.2. Maximum displacement is going to be plus or minus 1.7. And remember, acceleration is directly proportional to displacement, so that is a straight line. So I just need a scale. On the x-axis, I will say, here they have given us times 10 power negative 2. So I will just take maybe 10 small squares to represent 1 unit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 1 unit. I will call this 1.0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 2.0. And therefore this will be 1, 2, 3, 4, 5. This will be 3.0. I'll do the same this side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 1.0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 2.0, and it means this is going to be 3.0. So that is my scale on the x-axis. I just need the scale on the vertical axis. Note that the largest on the vertical is 5.2. That is the maximum displacement. So 5.2, I think I'll just take 5 small squares to represent 1 unit. So 1, 2, 3, 4, 5. That is 1. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is 1. This will be 2. This will be 3, 4, 5, and 6. So I'll do the same at the bottom. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 6 is here. So this will be -1, -2, -3, -4, -5, and -6. Here we have negative on the other side. So now I'm going to plot. I use a different color. Which color is very shouting? Can I use yellow? Okay. So on the x-axis, I need the positive and a negative 1.7. So this is 1.0 times 10 power negative 2. 1.1, 2, 3, 4, 5, 6, 7. So it is there. Then also this side, 1.7 is there. Then I now need 5.2 on both axes. The scale on the vertical, remember, is 1 unit is representing 5 small boxes. So I have 1/5, which is 0.2. One small box is 0.2 on the vertical, so I want 5.2. So 5.2, I will add one small square on 5. So I'm plotting a point which is 5.2 against. I don't have a ruler, so but I'm improvising. So 5.2 is against 1.7. I think this is the point. Yes. Also at the bottom, I have 5.2 against -5.2. I mean -1.7. 5.2 against -1.7. So 5.2, I add one small square, so you think it is here. Okay, so what remains now to draw the line? So I have plotted this point here. Of course, when the displacement is 0, the acceleration is 0. When the displacement is positive upwards, the acceleration is also positive, maximum, and so on and so forth. So that is a straight line which goes through the origin. And I just try to improvise with a ruler. I didn't carry my ruler, so I'm trying. Using a ruler, because you know that this is a straight line, so you can draw it very perfect. Sorry, because I'm not using a ruler, that is the problem. I'm just trying to improvise. This line is not very straight. It's not going to my points as I wanted. Just put the ruler and draw a straight line through the plotted points. Did I plot this point wrongly? Oh yeah, this point is not 5.2. It is actually 5. I think 5.2 is here. Okay. Okay, so I have tried my level best. It is not easy without a ruler, but I've tried. You can sketch a better one. So that is supposed to be a straight line. Note that your line does not go through beyond 5.2 plus or minus, because the maximum acceleration is going to be 5.2, either plus or minus. Acceleration is directly proportional to displacement. When displacement is 0, the acceleration is 0. The graph is through the x-axis, through the origin. When the displacement is maximum, that is 1.7 amplitude, the acceleration is also maximum 5.2. So you must the graph should not go beyond those points. That's why my line stops there. Okay, so you can also verify that. Calculate the displacement of the ball at which its kinetic energy is equal to half of the maximum kinetic energy. I think that is an easy question. So we want kinetic energy to be half its maximum kinetic energy. So kinetic energy, we know it is a half m omega squared into x naught squared minus x squared. So the kinetic energy must be half the maximum. Maximum kinetic energy is actually the same as maximum energy, which is just a constant, a half m omega squared x naught squared. Kinetic energy is maximum when the displacement is 0. The body is passing equilibrium. So we are equating a half m omega squared into x naught squared minus x squared to 1/2 of the maximum, that is a half of a half m omega squared x naught squared. So we have cancelled out a half m omega squared. We are remaining with x naught squared minus x squared being equal to x naught squared over 2. So we just collect we just want like terms because we want x. So twice x naught squared minus x squared is equal to x naught. So this is also twice x squared is equal to x naught squared. So we collect like terms. I take 2x one side, so you have twice x squared equaling 2. When I take x naught on the other side, it will be 2x naught squared minus x naught squared. So x squared is equal to x naught squared over 2. So I substitute to find the square root. So x is going to be x naught over root of 2, which is x naught is 1.7 in centimeters divided by root of 2. I press my calculator. So from my calculator, I get this as 1.2 centimeters. Okay. A mass of 78 grams is suspended from a fixed point by means of a spring as illustrated here. The stationary mass is pulled vertically downwards through a distance of 2.1 centimeters and then released. So this is going to be our amplitude. I'll use x naught for amplitude, maximum displacement. The mass is observed to perform simple harmonic motion of period, so the period is 0.69 seconds. The mass is released at t equals to 0. Remember, it is starting from maximum displacement. For the oscillations of the mass, calculate the angular frequency omega. We already know that omega is 2 pi divided by period. So this is easy. This is 2 pi divided by the period, which is 0.69. We just press our calculator. So this gives me 9.11. 9.11 or 9.1 if you wish. So I can say 9.1 radians per second. Determine the numerical equation for the variation with time t of the displacement x in centimeters. Numerical equation. Remember, they said it is displaced vertically to the distance of this and then released. It is released at time t equals to 0. So we are seeing that time t equals to 0 when it is at maximum displacement. And there are two solutions to the equation A equals to negative omega squared x. The first one can be x equals to x naught cos omega t, and the other one is x equals to x naught sine omega t. So which of these two equations gives us maximum displacement when t is 0? That is this equation here. When I put t equals to 0 here, x will be x naught. Remember, timing is starting when the body is at maximum displacement. But at t equals to 0 in the second equation, x is going to be 0. That would mean timing starts when the body is passing equilibrium. So the equation we need must be in the form of x equals to x naught cos omega t. We already have omega. We also have the amplitude as 2.1. So I'll just write this because they want x is in centimeters. I'll just say x equals to x naught, which is 2.1 cos 9.1 t. That is the first equation which they want. X is equal to 2.1 cos 9.1 t. Then the speed v in meters per second. The speed v in meters per second. So we also we can, if you're a mathematician, you can differentiate this equation. Since we have that x equals to x naught cos omega t, we differentiate this, we shall get the speed v, which is going to be equal to v naught. Of course, this will be times omega. This will be, okay, v naught sine. This will be v naught sine omega t. But note that v naught will be, the derivative of this is going to be, of course, v naught is going to be the maximum speed, which is going to be actually omega times x naught. So omega is 9.11 or 9.1 times maximum amplitude. Of course, here I have to change it. I have to change the amplitude to centimeters, so that is 2.1 times 10 power negative 2. So I'm finding V naught. V naught is going to be omega times x naught, which is equal to 9.1 times 2.1 times 10 power negative 2. And this is 0.19 meters per second. That is V naught. So V is going to be V naught sine omega t. So V is going to be equal to V naught, which is 0.19 sine omega is 9.1 times t. So the examiner would wish to see this and then that, and that will be fine. Okay. Then calculate the total energy of oscillations of the mass, total energy. Total energy, that is maximum energy, and maximum energy is a constant. We know that maximum energy Emax is going to be equal to a half m, a constant, omega squared, a constant, times x naught squared, which is also a constant. So we just substitute. So this is going to be a half times the mass. The mass was given as 78 grams, which is 78 times 10 power negative 3 to change it to kilograms. Omega was 9.1. So I'll say times 9.1 squared. Then x naught amplitude is 2.1 centimeters, so I'll say times 2.1 times 10 power negative 2, and this should also be squared. So just press my calculator. So this gives me 1.4 times 10 power negative 3. 1.4 times 10 power negative 3. Note that we could also use the expression for kinetic energy, half m v squared. But remember, when kinetic energy is maximum, potential is 0. So the total energy is the same as maximum kinetic energy. So this will be v naught, where v naught is the maximum speed, which we have got above. So this would also give us another value, an alternative method, that is a half times 78 times 10 power negative 3 times v naught, which we got above as 0.19, and this should also be squared. And I suppose it gives us almost the same answer as we have just done. A student investigates the energy changes of a mass oscillating on a vertical spring as shown here. The student draws a graph of variation with the displacement x of energy E of the oscillations as shown. So this is the graph of energy against the displacement. State whether the energy E represents the total energy, the total potential energy, or the kinetic energy. So remember, total energy is a constant. So that would be a horizontal line. So it can't represent, this cannot represent total energy. Total energy, E total, is equal to a half m omega squared x naught squared. All these ones are constants. Total energy is a constant. Potential energy, E potential, is equal to a half m omega squared x squared. Potential energy is directly proportional to x squared. So it means when displacement is 0, potential energy should be 0. That means this graph cannot be for potential energy, because we are seeing when displacement is 0, potential energy is actually maximum value. Then kinetic energy is equal to a half m omega squared into x naught squared minus x squared. And we see that when x is 0, kinetic energy is equal to actually the maximum energy, which is actually total energy. So this graph is going to be representing kinetic energy. So this one is for kinetic energy. Okay. Part B, the student repeats. The student repeats the investigation, but with a smaller amplitude. The maximum value of E is now found to be 1.8 millijoules. The maximum value of E is now found to be 1.8 millijoules. Use the figure to determine the change in the amplitude. Explain your working. So the maximum value is now 1.8 millijoules. Here the maximum was, what is this value? The scale on the vertical is 0.5 divided by 10, that is 0.05. So this is 2.5, I think. Okay, so the change in energy, let's see the change in energy here. The other one was 2.4 millijoules. Now this is 1.8 millijoules. So we can see that the change in energy is equal to 2.4 minus 1.8, which is 0.60 millijoules. That is the change in energy. And we know that maximum kinetic energy is directly proportional to amplitude squared. Maximum kinetic energy, we know that E total, E maximum, or E total, maximum energy, is directly proportional to amplitude squared, that is to x naught squared, which is the amplitude. So since this is the change in energy, then we can also believe that the change in amplitude is directly proportional. So I will just say, okay, that one divided by, okay, let me use a simpler method because the new amplitude here I'm getting 1.3, but it will not be easy for a non-mathematician. So if you're not a mathematician, let me use a simpler method for you. So when maximum energy E total is equal to a half m omega squared times x naught squared. When maximum was 2.4 millijoules, I will not change the units here. This was equal to a half m omega squared times x naught. Maximum amplitude was 1.5, that is times 1.5 squared. Then the maximum value of E is now found to be 1.8 millijoules. This will be a half. M has not changed, omega has not changed, times the new amplitude. The new amplitude is actually, I'm going to call it x naught squared. So I'm just going to divide these two equations. So I will have 1.8 divided by 2.4 is equal to x naught squared divided by 1.5 squared. So I'm getting the new amplitude when the energy is 1.8. So 1.8 divided by 2.4 times 1.5 squared, then root of the answer. So the new amplitude is x naught squared. The new amplitude is 1.299. So this is one. I've got the square root. So x naught is 1.3. X naught is 1.3. So if x naught is 1.3, then what is the change? Remember, the original amplitude was 1.5. So the change is going to be equal to 1.5 minus 1.3, which is 0.2. So the change is actually 0.2 centimeters. So if you're not a mathematician, you can use that. But non-mathematician can see that if maximum energy is directly proportional to amplitude squared, then, and yet we see that the change in energy is 0.60 millijoules, Then we can, using simple relations, we can see that the new amplitude is going to be 1.3. Okay, but this is a simpler method. This is a simpler method. If you're an able student, you can also use a simple relation relating to change in energy as being this, and see the corresponding change in amplitude. For an oscillating body, state what is meant by frequency. Of course, we know frequency is no, this is forced frequency, not necessarily a frequency. We know frequency generally is the number of complete oscillations per unit time. That is frequency, but this one is forced frequency. So we have a system which is capable of oscillating on its own, but then we subject it to a periodic force to keep it oscillating for a required period of time. The frequency with which such a system oscillates is what we call forced frequency. So it is the frequency at which an object is made to vibrate. It is forced to vibrate. So the frequency at which an object is made to oscillate or to vibrate. The object is not vibrating on its own, it is just made to vibrate on that frequency. It is just forced to vibrate on that frequency. So the frequency at which an object is made to vibrate is called the forced frequency. The natural frequency, here the object is not being forced, it is not being made to oscillate. It is oscillating on its own. So the frequency at which an object vibrates when free to do so is what we call the natural frequency. Frequency at which an object vibrates when free to do so. So that is what we call the natural frequency. There is no any other external periodic force acting to cause the body to vibrate. It is vibrating on its own. That is, the frequency with which it vibrates is its natural frequency. Then resonancy, when the forced frequency, when the forced frequency balances with the natural frequency of a system, the system is going to absorb maximum energy and vibrate with maximum amplitude, and we say that resonance has occurred. So resonance, this one occurs when natural frequency of vibration is equal to the forced frequency so here the system absorbs maximum energy and vibrates with maximum amplitude. So the system absorbs maximum energy, a lot of energy, and vibrates with the maximum amplitude. That's what we call resonance. State and explain one situation where resonance is useful. Of course, resonance is useful in many situations. Number one, you must have heard of microwave oven cooking, or you use microwave ovens at home. So microwave oven cooking. Number two, you must have heard of magnetic resonance imaging. Number three, we have seen resonance being used in quasi-crystals, in the piezoelectric crystals, for accurate timing or to maximize amplitude of ultrasound waves or to maximize production of ultrasound waves. So resonance is used in vibration of quartz, vibration of the quartz or piezoelectric crystal. This is normally for accurate timing or to maximize production of ultrasound waves. So those are some of the applications of resonance. Okay, in some situations, resonance should be avoided. State one such situation and suggest how the effects of resonance are reduced. By the way, in some situations, you have heard of the London Bridge, is it London Bridge? No, the Tacoma Narrow Bridge, which collapsed. So that means the effect of resonance could be sometimes dangerous. Therefore, sometimes it needs to be avoided. But the most common one are the vibrating metal plates. If you have heard of a generator vibrating, the metal plates are most likely going to cause to be damaged as a result of resonance. So vibrating metal plates are normally get damaged as a result of resonance. So we normally place strengthening struts. Those who will be doing engineering, you'll see what a strut is when houses are being roofed. There are ties and struts in the roofing structures. So what I mean by if these are two metal plates, this is one metal plate and another one. Instead of just putting them on each other, they put struts in between to minimize the effect of resonance. Excuse me. So vibrating metal panels or metal plates. Vibrating metal panels get damaged. So how do they said state one such situation and suggest how the effect of resonancy are reduced. So vibrating metal panels easily get damaged if resonance occurs, and this is reduced by placing strengthening struts across the panels. So place strengthening struts across the panels. You can place strengthening struts across the panels, or we change the shape or area of the panel. The area of overlap of the panels. So that will minimize damage. Okay. State what is meant by simple harmonic motion. I said this means acceleration is directly proportional. Motion is said to be simple harmonic motion if acceleration is directly proportional. Acceleration is directly proportional to displacement. Acceleration is directly proportional to displacement. Acceleration and displacement are always in opposite directions. Or you can say acceleration is always towards a fixed point. By the way, this fixed point is the equilibrium position. So acceleration is always directed towards the equilibrium position. Or you can simply say acceleration and displacement are always in opposite directions. That's why we have a minus sign in the equation A equals to negative omega squared x. Okay, the variation with the time t of the displacement x of two oscillators P and Q is shown here. Two oscillators each have the same mass. So they have the same mass. Use the figure to determine the phase difference between the two oscillators. We want the phase difference between the two oscillators. So phase difference is simply going to be, if I want to use, since I've been given, okay, it is required in radians, so I'll say phase is going to be equal to 2 pi into the time out of step over the time for one cycle. So time out of step, I will quote t over the time for one cycle, that is period. So this will be 2 pi into the time out of step. I will measure it from, let me see, okay, I'll take this point here and this one, corresponding points, that will give us the time out of step. So the scale on the x-axis is 0.04, that is 0.4 divided by 10. So this is 0.8848889. No, 88. That is 2.5 times 0.4. That is 2.5 times 0.4, that is 1. So that is 0.9. So here it is 0.9, and then here I'll just count 1, 2, 3, 4, 5, 6, 7.5. 7.5 small squares. 7.5 times 0.4, each small square is 0.04. 0.04. 7.5 times 0.04. So that is 0.3. I add it to 0.8 plus 0.8. That is 1.1. So that is 1.1. I hope this is 2.5 times 0.04. That is 0.1. So this was 0.9 and this is 1.1. The difference time out of step is going to be 1.1 minus 0.9. 1.1 minus 0.9, which is 0.2. So the time out of step is 0.2. Divide by the period. The period is, I think, 1.2. I can start from t equals to 0 up to here. That is one complete cycle. So the period is 1.2. So I will have 0.2 divided by 1.2 times 2 pi. So I have this as 1.05 radians. 1.05 radians. And I think this is the same as, let me see, as a fraction. As a fraction, this is, when I change this will be 2 over 12, that is 1 over 6. I mean, yes, 1 over 6. So this becomes pi over 3 in radians. So the answer here can be pi over 3 in radians or 1.05 in radians. Of course, in angles, pi over 3 is 180 divided by 3. It could be 60 degrees. That is the phase angle. Okay, that is the phase difference. I just needed the time out of step, the time in which one wave or one oscillator is ahead of the other. That is the time. You just get corresponding values of time and you get the difference in those points. It is always the same. It is going to be the same. I got 0.2. You can also check. Then the maximum acceleration of oscillator Q. Remember, acceleration is equal to negative omega squared x. Now, if it is maximum, x should also be maximum. Ignoring the negative in calculation, omega is 2 pi over t. So this will be 2 pi divided by the period is 1.2. But this should be squared times the maximum displacement of oscillator P, which I think is 3 centimeters. So that will be 3 times 10 power negative 2. So I now check my calculator. So from my calculator, this is 0.82. Okay. Then the ratio maximum kinetic energy of oscillations of Q over maximum kinetic energy of oscillations of P. So I'll just say that ratio equals to, remember, kinetic energy. Maximum kinetic energy is the same as total energy, which is a half m. Omega squared is going to be the same because the period is the same. X naught squared, but this will be for Q. Divide by a half m omega squared x naught squared, and this will be for p. Remember, what will be different will only be x naught. So half is the same, m is the same, omega is the same. So I only remain with x naught squared for q divided by x naught squared for p. So for q we have seen it is 3 centimeters, and then for p it is here in the center. It is there in the center. I think that is 1 point. Is it 1.7? The scale on the vertical is 1 divided by 5, which is 0.2. So you have 1, 2, 3, 4, 5, 6, 7, 8 and a half. 8 and a half, I'll just say 8.5 times the scale, 0.2. It's 1.7. So this is 1.7 in the center here, because the amplitude is here. So that is time over 1.7. I just press my calculator. Oh, by the way, this is squared and this is also squared. So from my calculator, the ratio is 3.1. 3.1. That is the ratio. Use data from the figure. Use data from B to sketch on the graph, on the axis, the variation with the displacement x of the acceleration. So we know that acceleration is equal to negative omega squared x. So acceleration is directly proportional to x. That is a straight line. But the negative means the line should have a negative gradient. Okay. We have seen that. Remember, we are sketching for oscillator Q, whose maximum displacement or amplitude was 3. So on the x-axis, our graph should not go beyond 3. And our maximum acceleration is 0.85. So we need to look for a scale on the vertical. 0.85. I mean 0.82. Is it 82? Yes. So we need a scale on the vertical for 0.82. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which scale should I use? There are 20 small boxes. Can I use 1, 2, 3, 4, 5? I'll call that one 0.4. 1, 2, 3, 4, 5. 0.8. That will be very small. Okay, let me just say within this whole range there is 1.0. 1.0, that means one small square is going to be 1 divided by 20. That is 0.05, I guess. 1 divided by 20, 0.05. Now I want to plot 0.82. I'll say 0.82 0.82. I will divide this by the scale. divide by the scale, which is 0.05. I think these are 16. 0.82 divide by the scale. This is 16.4. That is about 16.4 small squares, approximately 16 and a half. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 and a half, almost in the center there. So I will move 1, 2, 3. It is almost there. So 1, 2, 3. This is the point I'm going to plot. I'm going to plot 3 and 0.8582. Then I plot -3 and 0.8. So the 3 is negative that, then -3 is positive that. So 3 is going to be here, 3 against 0.82 is there. So I'm plotting these points. This one, of course, when displacement is 0, the acceleration is 0. And this one here. I'll have to pull out my ruler, which is not good. It's not a good ruler, but I will still use it. Okay, I think I've tried. You can also try to sketch and see. The line should not go beyond x naught. If it does, then you have changed the meaning of acceleration of simple harmonic motion. The line stops there at x naught. Okay, so that is precisely the line. It's not easy to sketch, but I've tried. Note that this was this maximum displacement, maximum acceleration, maximum displacement on the other side, maximum acceleration. Note that they are always in opposite directions. When displacement is maximum positive, the acceleration is maximum negative. State by reference to the displacement what is meant by simple harmonic motion. So we know that the acceleration is directly proportional to displacement but of course the two are always in opposite directions, or the acceleration is always directed towards the equilibrium position. So this time I will say acceleration and displacement are in opposite directions. Okay. A mass is undergoing oscillations in a vertical plane. The variation with displacement x of the acceleration a of the mass is shown here. Of course, when you look at this graph, you notice that acceleration cannot be directly proportional to displacement because it's not a straight line. Number two, you also see that the maximum acceleration is not the same on both sides. So this motion is not a simple harmonic. The maximum displacement is not the same on both sides. It is not simple harmonic. So the first question says state two reasons why the motion of the mass is not simple harmonic. So one, the graph is not a straight line. The graph is not a straight line. If the graph is not a straight line, we cannot say that acceleration is directly proportional to displacement. So the graph is not a straight line, so acceleration is not directly proportional to displacement. The number 2, maximum displacement. We have seen that the maximum displacement or accelerations are actually different. The maximum displacements or accelerations are different. For simple harmonic motion, the acceleration below and above the x-axis should be the same in magnitude. The displacement on the left and the right of the vertical axis should be the same if it is simple harmonic motion. So this one is not simple harmonic motion because the maximum displacements or accelerations are different. Okay. Use a block of wood is floating in a liquid as shown here. The block is displaced vertically and then released. The variation with the time t of the displacement y of the block from its equilibrium position is shown here. So you see that actually you notice that the displacement is decreasing exponentially. You can see that the displacement is decreasing exponentially as you could see. Use data from the figure to determine the angular frequency omega of the oscillations. So we know that angular frequency omega is equal to 2 pi divided by period. So, and we know that the period t is equal to, let's find the period from the graph. Time for one complete cycle, if I start from t equals to 0 at this point, then after one cycle I'll be here, and that is 0.8. Or you can start from this peak, which is 0.4, to this peak, which is 1.2. So the period is 0.8. So the period is 0.8 seconds. So omega is going to be 2 pi divided by 0.8. I just check my calculator here. 2 pi 0.8. So omega is 7.85. 7.85 radians per second. Then the maximum vertical acceleration of the block. Maximum vertical acceleration of the block. So acceleration is equal to negative omega squared x. Acceleration is maximum when displacement is maximum. So acceleration A naught, I will ignore the minus in calculation. So this will be 7.85 squared times the maximum displacement. I'll look at the graph and you notice that the highest displacement is 1.5, ignoring the negative. We can't take this as the highest. This is the highest we have. So the maximum displacement is 1.5 times 10 power negative 2 because it is in centimeters. So 0.78, sorry, 7.85 squared times 1.5 exponent negative 2. So this is 0.92. Have this as 0.92. It could be 0.93 depending on how you have done it. If you have done it like this, to get a more precise value, A naught is equal to omega, which is 2 pi over 0.8 squared times 1.5 times 10 power negative 2. This one has given me 0.92, but this one will give me a more value, a higher value slightly. 2 pi divided by 0.8 squared times 1.5 exponent negative 2. So this one would give you 0.93, but these will be, each of these will be accepted. The block has, but this one would be the most appropriate, of course, because you use the more exact value of omega rather than the first one. So I will take the second one as the best value, 0.93. The block has mass 120 grams. The oscillations of the block are damped. Remember, damping, loss of energy due to dissipative forces acting on an oscillating system. Calculate the loss in energy of the oscillations of the block during the first 3 complete periods. The loss in energy. So here we shall take total energy, and total energy, so I will just say loss in energy will be equal to a half. Now just write energy is equal to a half m omega squared times x naught squared. So that is total energy. So the change in energy, the loss in energy, delta E, is going to be a half. The mass is 120 times 10 power negative 3 times, I'll use, let me use 2 pi over 0.8, and this is squared as omega. Now the difference in amplitudes, initially it is 1.5, so this would be 1.5 times 10 power negative 2, and this is squared. Then after 3 complete cycles, let us see what is the amplitude. After 3 complete cycles, so this is 1 cycle, 2 cycles, 3. The third one is here, and the amplitude is 0.9. If you can see, the amplitude is 0.9. That is 0.9. So after 3 cycles, the amplitude is 0.9. So I will say minus, again, 0.9 times 10 power negative 2. This is also squared. So I just got the energy using the initial energy using this amplitude and the final energy using this amplitude. Then I subtract. That's why you see they are in the same bracket and subtracting, because all these other 3 quantities will be the same. I press my calculator. So my calculator is giving me 5.3. 5.33 times 10 power negative 4. I'll just write 5.3 times 10 power negative 4 to 2 significant figures. A metal block hangs vertically from one end of a spring. The other end of the spring is tied to a thread that passes over a pulley that is attached to a vibrator as shown here. So we have a vibrator attached to a pulley. There's a thread passing over a pulley attached to a spring, and the block is at the bottom. The vibrator is off. That means now the block is going to vibrate in its natural form. So its frequency will be the natural frequency. The metal block of mass 120 grams is displaced vertically and then released. The variation with time t of the displacement y of the block from its equilibrium is shown here. For the vibrations of the block, calculate the angular frequency omega. So we want omega. We now know that omega is 2 pi over period. All we need is the period from the graph. I think you can see that the period is 0.6. If we at equals to 0, we are this peak. After 0.6, we are coming back with the same peak. So the period is 0.6. So this will be equal to 2 pi divided by 0.6 seconds. When I press my calculator, so here omega is equal to 10.47, which is approximately 10.5 radians per second. Then the energy of the vibrations, of course, that will be meaning total energy. We have already now established that total energy E is equal to a half m omega squared times x naught squared. Total energy is a constant because all these ones are constants. So we want the energy of the vibrations. So the energy is going to be a half. The mass was 120 grams, so that is 120 times 10 power negative 3. Then omega is, I don't want to use 10.47, I will use 2 pi over 0.6. So this is 2 pi divided by 0.6, and this is squared times the amplitude. The amplitude of vibration is, amplitude I think is 2 centimeters. So this will be times 2.0 times 10 power negative 2, and this is also squared. I press my calculator. So I am getting 2.63 times 10 power negative 3 in joules. Or I will just write 2.6 times 10 power negative 3 in joules. The vibrator is now switched on, so it means the free oscillations are now over. What is happening is forced oscillations. The frequency of vibration is varied from 0.7 F to 1.3 F, where F is the frequency of vibration of the block in A. So F was the natural frequency. So for the block, complete the figure to show the variation with the frequency of the amplitude of vibration. So if F was the natural frequency and the frequency of the vibration is varying from 0.7, of the vibrator is varying from 0.7 to 1.3, it means when the frequency of the vibrator reaches F, it will be equal to the natural frequency of vibration. What happens? Resonance occurs. The system vibrates with maximum amplitude. So it means we shall have maximum amplitude at F. So this is a resonance curve which you must have sketched in your class. So we shall have a maximum amplitude at F. Okay, maximum amplitude at F. Then, so that is the resonance curve. Of course, as the frequency increases, the amplitude of vibration increases and is maximum when the frequency of the vibrator is equal to the natural frequency of the block. Some light feathers are now attached to the block. If we attach light feathers to the block, we put feathers to the block, we are increasing the surface area, so we are damping. So to increase air resistance, the frequency of vibration is once again varied between 0.7 to 1.3. The new amplitude of vibration is measured for each frequency. draw a line to show the variation with frequency of the amplitude of vibration. So when we increase damping, it means the amplitude of vibration reduces, because actually the system cannot vibrate with a lot of amplitude when there is a dissipative force. So it means the maximum amplitude is going to be lower. But also when we load the block with the feathers, we are reducing its natural frequency. It means maximum amplitude is also going to be reached at a frequency smaller than the one it was reached before. So it means we shall draw another peak, another graph whose peak is having a frequency to the left of the current frequency. So we shall sketch a peak here, a graph here below the first one. It will be more flatter. So you notice that the peak of this graph is somewhere here, which is actually to the left of the first peak. And you also notice that the peak of this graph is a little bit more flatter than the one of the first graph. So you need to capture that when you are sketching this. Something like that. The peak of the first one is a little bit smaller. The second one is a little bit flatter, more flatter than the first one. Okay. So you need to learn to sketch such simple graphs. Okay, next, the defining equation of simple harmonic motion is that. Identify the symbols in the equation. I think this is an easy equation. A is acceleration. And this omega is angular velocity or angular frequency. Then x is displacement. That is an easy question. State the significance of the negative sign. Of course, the negative sign indicates that acceleration and displacement are always in opposite directions, or it means that acceleration is directed towards the equilibrium position, or towards the mean position, or towards the center. So acceleration and displacement are always in opposite directions. Acceleration and displacement are always in opposite directions. A frictionless trolley of mass m is held in a horizontal surface by means of two similar springs, each of constant k. The springs are attached to fixed points as illustrated here. Show that the magnitude F of the restoring force acting on the trolley is given by this expression here. So let's look at these trolleys. If the springs are attached to fixed points as illustrated in the figure, show that the magnitude F of the restoring force acting on the trolley is given by F is equal to Kx. I think something is missing here, but let us assume that the trolleys are given a displacement x to say the left. If the trolleys are given a displacement x to the left, it means this spring here is going to extend by e, its extension will be e plus x, and this spring here, its extension will be e minus x, where e is the extension before an additional displacement x. So we shall simply say that the tensions in the springs, are, I'll call this one T1. So T1 is going to be equal to, remember by Hooke's law, F is equal to Kx or Ke. So the tension in the spring here is given by Hooke's law. So this is going to be K times the extension, which will be equal to E plus X. When the system is displaced X by a distance X to the right. For the second spring, the tension here I'll call it T2. And you notice that T2 is going to be K into E minus X. So the resultant force on the trolley is actually going to be the restoring force, which is going to be the difference in these two tensions. So I'll say that the resultant tension is going to be equal to K into E plus X minus K into E minus X. And you notice that this gives you Kx plus Kx, which is twice Kx. So this is going to be the resultant force. You just look for the tensions when the spring is, when the system is displaced, or when the trolley is displaced on one side through a further distance x. Of course, when it is not displaced, when it is in equilibrium, each of these springs experiences an extension E. Then when it is displaced further beyond equilibrium, the extension of one spring increases by that displacement x, and the other one compresses by the same displacement x. That's why you see on the left I added x, on the right I subtracted x. The trolley is then released. Show that the acceleration of the trolley is given by a is negative kx over m. So by Newton's third law, force is equal to mass times acceleration. The force is going to be negative 2kx. The reason, F acts in the opposite direction to the displacement. F acts in opposite direction to displacement. That's why you see I've brought in the negative. F was equal to 2kx here in the previous part, but notice that I considered the trolley being given a further displacement x to the right. The resultant force is actually to the left. So it means x acts in the opposite direction to the resultant force, or F acts in the opposite direction to the displacement. So we now use Newton's second law. So we shall say ma is equal to negative 2kx, where when we make a the subject, we see that acceleration is going to be equal to negative 2kx divided by m. So these are only 2 marks. 1 mark will be for that, and the second mark will be for appreciating that you are using Newton's second law. The mass m of the trolley. Do not forget, by the way, to define why you have brought in the negative, which was not there in the first part. The mass m of the trolley is 900 grams, and the spring constant K is 120 newtons per meter. By comparing your answer to A Roman 1 and the equation in B Roman 2, determine the frequency of oscillation of the trolley. So we are just going to compare. So we have that A is equal to negative twice K x over m compare with A equals to negative omega squared x. So you will notice that therefore omega squared is equal to 2k divided by m. But remember omega is 2 pi f, so we shall say that 2 pi f or 2 pi over t, 2 pi f is squared is going to be equal to 2k, and k is given as 120 spring constant. Then over m, the mass is 900 grams. 900 grams is 0.9 in kilograms. So I want F. I just press my calculator. 2 times 120 divided by 0.9. I find the square root because on the left it is squared. Then I divide by 2 pi. And this gives me F as 2.9, sorry, not 2.9, 2.599, approximately 2.6 hertz. That is the value for F, approximately 2.6 hertz. Suggest why the troll in B provides a simple model for the motion of an atom in a crystal. Why does it provide a simple model? So first of all, we know from AS, particle physics, we know that atoms are held by attractive forces, or atoms are held by forces, and they just, in solids, they don't move, they simply vibrate above their equilibrium position. And in this model, we are seeing that actually the trolley is held on both sides by springs and just moves in that direction, along that same fixed point. But also remember, this motion is only in one dimension, yet the vibration of atoms is in 3 dimensions. This model gives a motion in one dimension, a straight horizontal line, yet atoms vibrate in 3 dimensions. So it's not just it is not giving a very good model. It is maybe a simple model, but not a real model of the atoms. So we can say we can accept and we can also disagree depending on what you want. So we can say atoms or an atom in a crystal is held in position by attractive forces and the atom oscillates. So this one is in agreement. But on the other side, we can disagree. Here we have said, okay, an atom in a crystal is held in position the same way that trolley has been held. It is held by attractive forces and the atom oscillates the same way that trolley was oscillating. But on a reverse argument, we can give details, or it's not just two forces that act on an atom. It's not just two forces. It's not just two forces. It's in 3 dimensions, not one dimension as we have seen. And for atoms in a crystal, I don't think force is directly proportional to displacement. Force is not proportional to displacement. In an atom, the force on the in a crystal, the force on atoms on an atom is not directly proportional to displacement. Actually, in an atom, vibration is in 3 dimensions. It is not in 1 dimension as the model suggests. It's not only two forces acting as the model suggests, so it may not provide a good model for motion of an atom in a crystal. So you can be on one side with the statement, or you can reject the statement. A student sets out to investigate the oscillation of the mass suspended from the free end of a spring as illustrated here. The mass is pulled down and then released. The variation with the time t of the displacement y of the mass is shown in the figure. So they've showed us the graph of displacement against time. Use the information from the figure 3.2, which is the graph, to explain why the graph suggests that the motions are undamped. They are not damped. You see that the amplitude is constant throughout the motion. So constant amplitude. If the amplitude is constant, then we cannot think about damping there. Then use the figure to calculate the angular frequency, that is omega. We now know that omega is equal to 2 pi divided by period. So we check for the period here. So if I start from I just want a point which is perfectly aligned. If I look at this is the center. If I started from here, I think this is 0.75. So without hesitation, the angular frequency is going to be 2 pi divided by 0.75. I press my calculator. 2 pi divided by 0.75. So this is 8.4 or 8.377. I'll just write 8.4 radians per second. Then use the figure again to determine the maximum speed of the oscillating mass. The maximum speed of the oscillating mass. So of course, maximum speed can be found at the point where the graph is crossing the x-axis, which can be got from the gradient. If you want, you can get it from the gradient by drawing a tangent there. You draw a tangent at that point and find a gradient, because this is a displacement against time graph, and from AS we can use the gradient, but me I will not use the gradient. So you can use the gradient. That is an assignment. But me I know that maximum velocity Vmax is equal to omega. Now this will be times maximum displacement. Since I have omega in the previous part, maximum displacement will be equal to omega, which is 2 pi divided by t, which is 0.75, then times maximum displacement from the graph. Maximum displacement is 2 centimeters? Yes, 2 centimeters. Maximum displacement is 2 centimeters, so this will be 2.0 times 10 power negative 2. Remember maximum velocity, we said when velocity is equal to omega square root of x naught squared minus x squared. Velocity is maximum when the body is passing equilibrium, that is when x equals to 0. So when x equals to 0, V is maximum, and it was omega times x naught from that expression. When I put here 0, I remain with the root of x naught, which gives me maximum velocity as that. So from my calculator, so I'm getting this one as 0.168. 0.168 meters per second. Determine the resonant frequency F0 of the mass spring system. Resonant frequency. Resonant frequency is the driving frequency which is matching with the natural frequency of vibration. Driving frequency matching the natural frequency of vibration. Of course, this we just get it from the graph. We know that omega is equal to 2 pi. Omega is equal to 2 pi f. So the frequency is going to be omega, which is 8.4 divided by 2 pi, or I can just get f equals to 1 over t, 1 over the period, which is going to be 1 divided by 0.75. I think that is even easy. 1 divided by 0.75. This gives me 1.33. So the resonant frequency is going to be 1.33. When the frequency of the driver is equal to the natural frequency, then that frequency of the driver is going to be called the resonant frequency. This would give you almost the same thing, 1.3 hertz. The student finds that if short impulsive forces of frequency a half F0 are impressed on the mass spring system, in other words, we are adding periodic forces on the mass spring system, a large amplitude of oscillation is obtained. Explain this observation. So, periodic forces are added to the oscillating system. It means they are adding energy. They are adding energy to the oscillating system, and that energy, since energy is directly proportional to amplitude squared, it means that energy is going to be adding. It is going to be seen as an increase in amplitude. So we can say at a half F0, the pulses, the impulsive forces provided to the mass or they provide to the mass some oscillations. Provided to the mass some oscillations or some oscillating energy. So the pulses are going to build up, or the energy of the pulses build up to form a large amplitude. So energy of the pulses build up to form a large amplitude. Energy of the pulses build up to form a large amplitude. Because the periodic pulses are giving the mass an alternative oscillation or alternative oscillations, then the energy of the pulses build up to form a larger amplitude. The bar magnet of mass 180 grams is suspended from the free end of a spring as shown here. Okay. The magnet hangs so that the one pole is near the center of a coil of wire. The coil is connected in series with the resistor and the switch. The switch is open. Of course, when the switch is open, the magnet will now be having free oscillations. But of course, we know from magnetic fields, if we close the switch and the magnet is oscillating, then its oscillations are going to die out because an EMF is going to be induced in the coil, and energy will be dissipated in the resistor because energy is dissipated in the resistor, and that energy is derived from the oscillations of the magnet. Then the oscillations of the magnet are going to die out. That's why in the next part we see a graph of this nature. The magnet is displaced vertical and then allowed to oscillate with one pole remaining inside the coil. The other pole remains outside. The coil is connected in series with the resistor and the switch. The switch is open initially. At time t equals to 0, the magnet is oscillating freely as it passes through the equilibrium position. So at time t equals 3 seconds, so here we see that the amplitude is constant because there were free oscillations. At time t equals 3 seconds, the switch in the circuit is closed, and we see that the amplitude is gradually decreasing. That is, the system is now losing energy. The variation with the time t of the vertical displacement y of the magnet is shown in the figure. Okay. Determine to two significant figures the frequency of oscillation of the magnet. So to find the frequency, we need the period. Frequency is equal to 1 over period, and the period is going to be the frequency will be 1 over. Let's try to find the period. So I see that in 3 seconds, we have 2.5 cycles. So the period is going to be there are 2.5 cycles in 3 seconds, so the period is going to be 3 divided by 2.5. So the period, let me write it here, whatever way you find the period, but the period is going to be in 3 seconds, we have 2.5 cycles, so that is the period. So the frequency is going to be 1 over that period, which is now going to be the reciprocal of this value, so that will be 2.5 over 3. When I press my calculator here, so the frequency is 0.83 Hertz. State whether the closing of the switch gives rise to light, heavy, or critical. That is light damping. Why is it light damping? You see that the amplitude is just gradually decreasing. The oscillations are still going on, but the oscillations are occurring at smaller maximum displacements, as you can see. So when the amplitude gradually decreases, when oscillations are still continuing, then that is a light damping. Remember I said for heavy damping, there is no oscillations. For critical damping, there are no oscillations. The system just gradually goes to equilibrium without oscillation. So if it was light damping, there will be no these oscillations, and therefore the system will just go to equilibrium. In critical damping, it goes in the shortest time possible. In heavy damping, it may take more time, but there are no oscillations in both cases. Calculate the change in the energy of oscillation of the magnet between t equals to 2.7 and t equals to 7.5 seconds. Explain your working. Note that this is 6 marks. So let's first find the amplitudes, because we know that energy is going to be equal to a half m omega squared x naught squared. And of course we know that omega, of course we have found omega, we know the frequency, we know that omega is equal to 2 pi times f. So we just need to find x naught for 2.7 and 7.5. Then we shall get the difference in those two values. So we find at t equals to 2.7 seconds, what is x naught? Let's check from the graph. 2.7 seconds, I think x naught is maximum. 2.7 is around here. X naught is maximum, 1.5 centimeters. So at 2.7, x naught is 1.5 centimeters. So we can find the energy here. So energy in this case is going to be a half times the mass. What was the mass? What was the mass? I think they gave us the mass as 180. Was it 180 grams? A mass of 180 grams. Okay. So the mass is 180. 180 divided by 1,000. I think that is 0.18. Omega is going to be 4 pi, or I can say 2 pi f. So it will be 2 pi times f, which is 0.83, and that is squared. Then times x naught, which is 1.5 times 10 power negative 2. This is also squared. So this is the energy at that time. I'm also going to find the energy at 7.5 seconds. So let me check this one. So from my calculator here, the energy is 5.51 times 10 power negative 4 joules. I'll check also at time t equals to 7.5 seconds. What is x naught? 7.5, let's check on the graph. At t equals 7.5, I think it's almost in the center here. It is here in the center. And by looking at the scale, it is in the middle there. I think that is 0.75 because it is in the center between 1 and 0.5. So that is 0.75 centimeters. So at 7.5 seconds, x is 0.75 centimeters. So the energy here is going to be a half times 0.18 times 2 pi times 0.83 squared times this is going to be 0.75 times 10 power negative 2, and this is also squared. So I'm finding the energy here. So this is 1.38 times 10 power negative 4 joules. So that is the energy there. So we want the change. So the change in energy, I will just say the difference in energy is going to be 5.51 minus 1.38 times 10 power negative 4, which gives us 5.51 minus 1.38. So this gives us 4.13 times 10 power negative 4. So the change here is 4.13 times 10 power negative 4 joules. So those are the 6 marks. There's nothing much there. A cylinder and a piston used in a car engine are illustrated in the figure here. Okay. The vertical motion of the piston in the cylinder is assumed to be simple harmonic motion. The top surface of the piston is at AB when it is at its lowest position, CD when it is at the highest position. So AB is the lowest, CD is the highest. The displacement D of the piston may be represented by the equation D equals to negative 4 cos 220 T. So it is starting from the negative part, where D is measured in centimeters. D is in centimeters. State the distance between the lowest position and the highest position, CD, of the top surface of the piston. So the max, if it starts from at t equals to 0, it is at -4. So that is very easy. If at t equals to 0, it is at negative. Okay, just maybe compare with x equals to x naught cos omega t. So at t equals to 0, it is at -4. So maximum amplitude is 4 centimeters. So x naught is 4 centimeters. But we want the distance between the lowest and the highest. That means it is twice, because the lowest and the highest, that is half a half a cycle. If we move from the lowest to the highest, that is half a cycle. So the distance is going to be twice. The distance is going to be twice, that is 2 times 4.0, which is giving us 8.0. Alternatively, we can go back here. If we start from, let's sketch a simple graph of displacement with distance. So we start from here. So this is at -4. So this should be at +4. So the difference between the highest point and the lowest point is going to be -4 minus -4, which is actually 8. 4 minus -4, which is 8. Okay. Determine the number of oscillations made per second by the piston. Of course, that is the frequency. We know that omega is equal to 2 pi times f. And f is going to be omega divided by 2 pi. And omega, what is omega? Omega, we see it from here, it is 220. So omega is going to be 220, then divided by 2 pi. We just press our calculator. So from my calculator, this is 35 hertz. This is 35 hertz. So the number of oscillations per second is 35, or the frequency is 35 hertz, or 35 per second. Then on the figure, draw a line to represent the top surface of the piston in the position where the speed of the piston is maximum. Remember, speed is maximum at equilibrium, where the displacement equals to 0. So speed is maximum at equilibrium where the displacement equals to 0. So the speed will be maximum at the center. So we shall draw a line in the middle point. That is, we're going to try and estimate the center of this. I hope it is this point here. It is just at the midpoint. That is where we have our center. Displacement is, speed is maximum when displacement is 0. That is when the body is passing equilibrium. So I'm trying to look for the center, the midpoint. That's where I draw the line. I hope I've tried my level best to estimate the center. If I haven't, you can try to ensure that the line is at the midpoint. If you can take measurements, then it will be fine to see the exact midpoint. Okay, so that is the line they were looking for. Calculate the maximum speed of the piston. Maximum speed of the piston. So remember, speed is maximum when displacement is 0, and maximum speed V is equal to omega times x naught, or maximum displacement. So this is going to be omega, which is 220. Maximum displacement from the equation is 4 centimeters, so it will be 4 Since they want the answer in centimeters, I will not change. So it will be 220 times 4 centimeters. And I think this is obviously without even pressing the calculator, it is 880. 880 centimeters. The engine of the car has several cylinders. 3 of these cylinders are shown in the figure here. X, we have seen it. X is the same cylinder and piston as in the first figure that we have seen. Y and Z are 2 further cylinders with the lowest and highest positions of the top surface of each piston indicated. The pistons in the cylinders each have the same frequency of oscillation, but they are not in phase. They are not in phase. At a particular instant in time, the position of the top of the piston in cylinder X is as shown again, as shown there. In cylinder Y, the oscillations of the piston lead those of the piston in the cylinder X by a phase angle of 120. Complete the diagram of cylinder Y for this instant by drawing a line to show the top surface of the piston. Let's find phase difference of 120. Note that we saw that for cylinder A, the equation was D. I want a space here. Okay, I'll write here. We had that D is equal to negative 4 cos of omega, which is 220 times T. That's what we had. That means at T equals to 0, if we consider A, at T equals to 0, it was at the bottom where this was negative 4. And at the top, that was positive 4. From the bottom to the top, that is half a cycle, which is 180 degrees. So let's check. If y leads x by 120, what is the displacement of y from equilibrium? From equilibrium position, remember here at t equals to 0, the displacement was negative 4 for x. From equilibrium position at t equals to 0, let's see, d is going to be negative 4 cos of 220t plus the phase difference, which is 120. Let's find d from the calculator at t equals to 0. Remember, we are looking at x and y at the same time. So at t equal to 0, what is d for y now? At t equals to 0, I'm putting t equals to 0, so this will be 220 times 0. I just remain with the cos of 120. Cos of 120 is a half times negative 4, which is 2. So D is going to be 2 centimeters, and this is positive. So that means it's 2 centimeters above equilibrium. Note that equilibrium is at the midpoint of this. Equilibrium is around here. Equilibrium is around there. So 2 centimeters above, it is positive, so it is above equilibrium. So I will come to my graph, my diagram, and look for 2 centimeters, which is almost, I think 2 centimeters above is almost here. If you have a ruler, you can measure and divide this into equal divisions so that now you can easily estimate 2 centimeters will be, this is 2 centimeters. If this is the equilibrium position, here where x is 0, let's say this is x equals 2 centimeters. So this is the line we want, 2 centimeters above equilibrium. And 120 degrees, I think from moving from A to C, that will be 180 degrees out of phase. So it means if it is leading by 120 degrees, then it must be moving upwards. It has not reached CD. So the second part is saying an arrow. We have finished the line. An arrow to show the direction of movement of the piston. So this should be upwards. So the arrow is going to be here, upwards. Okay. Then part 2, in cylinder Z, the oscillations of the piston lead those in cylinder X by 240. Still, we can find a displacement at t equals to 0 of Z in comparison with X. So D equals to -4 cos of 220t plus the phase difference, the phase angle, which is 420, because Z leads X by 240. So we now check at t equals to 0. If we look at the two at t equals to 0, for Z to be at -4, for X to be at -4, how about for Z? Z will be at a displacement of -4 cos of 240. So we can check this. Cos of 240 is -0.5 times -4. It is also 2 centimeters. So it is above, it is positive. D is positive. It is also 2 centimeters. It is positive. It means it's above equilibrium. So we come back here in Z. So again, the new line will be also 2 centimeters above equilibrium position around here. 2 centimeters above equilibrium position. So you draw a horizontal line above, 2 centimeters above. Of course, this is not drawn to scale. That's why I'm just trying to use calculations to see. Note that from the origin, if this is 0, this is -4, and the other one is 4. So it means in between 0 and 4, that is 2 centimeters. But remember, this one is 240 degrees out of phase. And remember, from AB, that is 180, coming back, that is 360. So if I move from A to B, AB to CD, that is 180, and I'm coming back. 240 is when I'm going downwards. So it means the arrow in this case must be pointing downwards. 240, it should be going downwards in the opposite direction. So they said an arrow to show the direction of movement of the piston. So that will be downwards. So we have now attempted that abstract equation very well. We have drawn the line as required and the arrow. Drawn the line as required and the arrow. For this piston, for the piston in cylinder Y, calculate its speed for this instant. So we want to calculate the speed for that instant for the cylinder for the piston in cylinder Y. We have we want the speed at that instant. Remember, the displacement is 2 centimeters. So speed is generally given by omega square root of x naught squared minus x squared. So we have omega is 220 square root of x naught. The amplitude is 4 centimeters, so I will say 4.0 squared minus x at that instant in y. X, we have seen the displacement is 2 centimeters, so this will be 2 squared. Since the answer is in centimeters, I didn't try to change the units of displacements. So this is from my calculator. So from my calculator, this is 760 centimeters per second. It's actually 762, but I just wanted to write two significant figures. 760 per centimeter. I think this is enough for part 2. I would like to stop here for part 2. Watch out for part 3, and I hope you enjoyed this. Do not forget to subscribe. Thank you and stay blessed.